I'm delighted to welcome Jinyoung Park to our first session this fall semester. She's the winner of the Mariam Mirzakhani Award, and we're really thrilled to have her give a talk. Thank you.
Thank you very much for this invitation and this friendly atmosphere, and thank you for all of your help to make this talk start. So today I'm going to talk about counting homomorphisms from bipartite graphs, and this is joint work with Lina at Iowa State University and Gwen McKinley, who unfortunately left academia, and now she's at probably shortly starting her new job at Center for Communications Research, and this is Lina, and this is Gwen. So we conducted this research. This research is supported by MSRI, and they have very nice summer research program, and they support our travel, our lodging, and our meals. So it was very nice opportunity, and I'm just advertising because I was benefited a lot by them. So let me start. How can I start? Down, up, and it. Okay. Now it works. Okay. So this is our main result. Our main concern is the number of proper vertex Q colorings, where Q means the number of colors that we have, and we always assume that Q is a constant. Of the middle layers of the Hamming cube, and okay, so I think this sounds a little bit too much. Middle layers of the Hamming cube. Why do we care about that? And I'm gonna give you some of the backgrounds in later of the talk, but just visual. The Hamming cube looks like this, and I'm gonna give you the formal definition later. So it's the three-dimensional. Sorry, okay. So this is my first time in a while that I speak in English. So I'm still in my Korean mode. So please understand. So this is the visualization of the three-dimensional Hamming cube, and it has 8 vertices. And when we say the middle layers, that means we just focus on the middle part. And if we have like n-dimensional Hamming cube, then it's a huge structure. And we just look at the middle layers of the Hamming cube, and we say n is odd, just because in this case, there are exactly 2 middle layers. So in this case, we have a bipartite, so the middle layers for a bipartite graph. So in this case, we just focus on this induced bipartite graph. Sorry, this bipartite graph induced by the middle layers of the Hamming cube. Okay, and then our main result is this. For any even integer Q, the number of proper Q colorings of the middle layers of Hamming cube is asymptotically what it should be. And I'll talk about what it means by what it should be. But at this stage, a very interesting open question is what happens if Q is odd? So our result only covers the even number of colors, and still we do not know what happens when we have odd number of colors. And okay, so then what does it mean by what it should be? And there is a reason why I hide this result, because the result looks like this. So it's the asymptotic formula. So we say CQG for the number of Q colorings of G, and we are going to use BD for the graph that we are focusing on. And then the result looks like this, and I'm not sure how you feel about this, but I think this is not very beautiful, so I want to hide it. And eventually, this formula will not be very important until at the end. So let me just hide it. So let me just start from some early history for a soft start. Okay, so the history of this line of work goes back to like Dedekind's problem that is posed in 1987. And he asked what's the number of anti-chains of the Boolean lattice 2 to the n. And okay, so are we okay with the name Boolean lattice 2 to the n? This is okay, right? Okay, so this problem is formulated in the language of anti-chains, but as far as I know, the question that he asked is not the number of anti-chains, but the number of monotone Boolean functions on n variables. So when we have this 7 cube, and then we have the empty set at the bottom for, let's say this is 0 vector, and this is 1 vector, and then we have n variables. And then a monotone Boolean function looks like this. So they are all assigned 1s, and they are all assigned 0s. So this is the output of a monotone Boolean function. And then Dedekind was interested in what's the number of monotone Boolean functions on n variables. And then so this is a monotone Boolean function, but if we just take all of the minimal elements in this set, then this just form an anti-chain. So this counting monotone Boolean functions is equivalent to counting the number of anti-chains in 2 to the n. Okay, so this was his question, and then himself counted like for the number of anti-chains for small n's. So for example, when n is 0, then we have a singleton. And in this case, what's the number of anti-chains? There are 2 anti-chains because the empty set or the singleton. And when n is 2, when we have, sorry, n is 1, when we have one-dimensional Hamming cube, and that looks like this. So in this case, what's the number of anti-chains? We have, 3. So here the answer is here. And then when we have 3-dimensional Hamming cube, then we have 6 anti-chains, and etc. And then himself counted until 1, 2, 3, 4-dimensional Hamming cube, and then he got the answer 168, and then he stopped. And then he, I don't know whether I should say he gave up. And then at the end of his paper, he just said, it seems like this function is very rapidly growing. So, and then people, it seems people cared about his problem. So people made some developments on the number of anti-chains on n variables. And there was a recent development. So this is an article in the Quantum magazine very recently. So very recently, the 9th dedicated number was found by 2 independent groups. And so I think help is one group, and those 2 mathematicians are the second group. And then the 9th dedicated number is here, this number. And so I skimmed the article, and it says that for one group, it took 28 days to finish the computation. And for the other group, it took 3 months to finish the computation to get this number. So it's really rapidly growing number, and we don't know what is the 10th dedicated number yet. And maybe our current technology is not enough to compute this in a feasible amount of time. So this is very hard to compute the exact dedicated numbers. Then what do we do? Do we stop, or what do we do in this case? And this is a quote of Jordan Ellenberg that I like. So he said that a basic rule of mathematical life is if the universe hands you a hard problem, try to solve an easier one instead, and they hope the simple version is close enough to the original problem that the universe doesn't object. So I mean, we all agree with this, right? So in this case, if finding the exact dedicated number is so hard, then what we can try to do is to find asymptotic formulation of the dedicated numbers. So what happens to the dedicated number if n is very large? Then can we find the growth rate? So this is what we do. So for the dedicated problem itself, the asymptotics was already proved in 1980s by Russian mathematicians Korshunov and Sapozhenko. And so here I didn't put the asymptotic formula because it's still ugly. So I didn't want to put that, but we will talk about what we are focusing on is the number of independent sets in the Hamming cube, which was proved by Sapozhenko. And so again, we do not know the exact formula for the number of independent sets in the Hamming cube, but we do know Sapozhenko did prove the asymptotic formula for the number of independent sets in the Hamming cube. And the main tool is now called Sapozhenko's graph container lemma. And probably, I think the more famous one, currently the more famous one is the hypergraph container theorem, if this audience is familiar with that. But if you look at the date, then graph container comes much before the hypergraph container lemma. And yeah, I don't know like whether the group who proved the hypergraph container lemma was inspired by this or not. I don't know that. Okay, so let's talk about the number of independent sets in the Hamming cube. So now finally, let me give you the formal definition for the Hamming cube. So the Hamming cube is the n-dimensional Hamming cube. We're gonna write Qn, and the vertex set of the Hamming cube is the binary strings of length n. So for example, in this 3-dimensional Hamming cube, we have binary strings of length 3. And then, of course, the number of vertices in Qn is 2 to the n. And we're going to use big N for the number of vertices. So big N always means the number of vertices in the Hamming cube. And then the adjacency is defined by So x is adjacent to y if and only if they differ in exactly one coordinate. We all know this, I guess. Okay, good. So I don't have to explain to the death, right? Okay. So we know that Qn is an n-regular bipartite graph on E union O, where E means the set of even vertices and O is the set of odd vertices. And because we are interested in finding the asymptotic formula, so we assume that n is very large and goes to the infinity, but still finite. And then the asymptotic formula for the number of independent sets in the Hamming cube is this. So this is asymptotically 2 to the n over 2 times 2 times square root of E. So it's pretty interesting that we see this irrational number E here. So it's involved with the number of independent sets. Okay, so then let's see why it's natural to have this number for the asymptotics for the number of independent sets in the Hamming cube. And okay, so I'm sorry, Abigail, you have seen this thousands of times, right? Okay, so first, the trivial lower bound for the number of independent sets in the Hamming cube is 2 times 2 to the n over 2. Do we see why? It's very simple because so Hamming cube is the bipartite graph, so it looks like this. And then this is balanced, which means we have n over 2, many vertices in each side. So then how do we have 2 to the n over 2? Because this is bipartite, any subset of one part is an independent set, right? So from here, so by taking a subset of this part, we already have 2 to the n over 2, many independent sets. Okay? And then why do we have 2? Because we have 2 parts. Yeah. So this 2 times 2 to the n over 2 is a trivial lower bound on the number of independent sets. Then why do we have that extra factor square root of E? And here is an explanation. So again, this square root of E is rather easy lower bound asymptotically, and this is the explanation. So in this construction, I said whenever we take a subset of one part, then it becomes an independent set. But there can be more independent sets. What does it look like? Maybe we can take some of the vertices in the independent set on the other side. Yeah. And then because we have one vertex here and one vertex here, so their neighbors cannot be occupied. Where occupied means they're in the independent set. And then so we have to exclude those vertices, but the other vertices, but the vertices outside of this neighborhood, they have free choices. They can be in the independent set or not in the independent set. So each vertex in this shaded area has 2 choices, whether you count it in the independent set or not. So this way, we can construct more independent sets than the subsets of one part. So this is the computation. So we assume that we have k many occupied vertices in one part, and then we exclude their neighbors, and we just count, and then the rest of the vertices have 2 choices. This way, the number of such independent sets is approximately, first we choose k vertices out of n over 2 vertices, and then we exclude their neighbors. So k times n many vertices are excluded from this part. So we have this many choices for the other part of the vertices. And then, so this is asymptotic. Let me just skip this computation, but this like approximately gives us 2 to the n over 2 times 2 to the negative k over k factorial. So another lower bound is we can add them up. We can add up this formula for all of the k's. This way, we have this computation, and then if I hide this, then we have summation 2 to the negative k over k factorial. What is this? This is a Taylor expansion of e to the negative 1/2. So we, e to the 1/2. We have this.
So just considering the middle layer here?
Oh, no. So, okay, so this is for the entire Hamming cube. So that's why we have n regularity. Because if you just consider the middle layers, then the degree is about n over 2. But here, n-dimensional Hamming cube, so we have a degree n. So this is n. Yes. So are you okay with this construction? So to
ask what is the k that achieves this quality? Which choice of k, right? So you're saying that.
Oh yeah, so everybody has some like non-trivial contribution unless k is very large. So so eventually we have.
Something like a box attention. What is K in the oh, that's not.
I don't know. Maybe you can differentiate this expression. I haven't checked. Yeah, I haven't checked that. So okay, well, you can do it, or everybody can do it. So are you okay with this lower bound, asymptotic lower bound? Okay. So then the real meaning of Sapozhenko's result is this lower bound is actually the truth. So I think that's the interesting point. So getting lower bound is just easy, but the hard part is to show that this lower bound is actually an upper bound. Okay, so this is what I just said. So this is easy to show that this is an asymptotic lower bound. And then the real task of Sapozhenko was to show that this easy lower bound is actually asymptotically correct. So this is a picture of like that describes his work. So let's say this circle is the collection of all of the independent sets, and then we have a lower bound. We have some construction that gives an easy lower bound on the number of independent sets. And what it showed is all of the parts outside this easy construction is negligible. So I want to emphasize that asymptotic enumeration is not just about counting, but rather I see it as figuring out the typical structure of the given mathematical object. So here, the mathematical object that we're interested in is the collection of independent sets. And by showing that this part is negligible, what we can see is actually this is the typical shape of independent sets in the Hamming cube. So this gives us the typical structure of the mathematical object or the collection of independent sets. And because of this, we can also connect this to efficient sampling or approximating algorithm, because once we know that this part is negligible, and if we can quantify that, then we can say that, oh, instead of sampling independent sets from the entire collection, we can just sample independent sets from this easier collection, which we have a very, very good understanding about. So yeah, this can be used for efficient sampling or approximating. Okay. And then, okay, so this is about independent sets, but our work is related to figuring out the typical structure of cube colorings in the middle layers of Hamming cube. Okay, so this is all about the asymptotic enumeration that I'm doing. Do you have any questions? Or am I going too fast or too slow? Is this okay? Okay. Are we okay? Can we move on to the next slide? Okay. Okay, so today's topic is not independent sets, but graph homomorphisms, or it is sometimes called H colorings. But let me give you the formal definition. So what is a graph homomorphism? That is a map defined from the host graph G to a target graph H. And the requirement is every edge is mapped to an edge in H. So edge in G is mapped to an edge in H. That's the requirement for a graph homomorphism. Are we all familiar with this definition? Okay, very nice. So for example, if H looks like this, in this case, the corresponding homomorphism is an independent set in G. Are you okay with this? Or well, should I maybe yeah, you're too, I mean, maybe there are some audience on the Zoom meeting. So let me explain why this is an independent set. I'm gonna skip the rest. So in this case, let's say we have a graph like this. So this is our G. And in this case, okay, so consider a map from this graph to this graph H. And in this case, let's say this one is labeled, let's say 0. Then because an edge must be an edge in graph H, so that means 0 can be adjacent to any of both of 0 or 1. Because 0, 0 is an edge and 1, 0 is also an edge. So it can be 1, 1, 0, 0, and there's no restriction on this. On the other hand, once we have 1, then it can be only adjacent to 0. Because 1, 1 is not an edge here. So in this case, so it can be 0, 0. So 1 cannot be adjacent to another 1. So at the end of this, like when we look at this map, if we collect all of the 1 labeled this, then this forms an independent set. So every homomorphism from G to H is corresponding to an independent set on G. Okay, so this is how we translate an independent set in the language of a graph homomorphism. And if our target graph H is a clique on K vertices, in this case, each graph homomorphism is corresponding to a proper K coloring of the vertex. Are we okay with this? Because in this case, okay, a color cannot be adjacent to the same color. And if H looks like this, so this is an infinite graph on Z with roots on every vertex. In this case, the corresponding graph homomorphism is a Lipschitz function on the graph G. Are we okay with this? Because once we have an assignment on a vertex, then all of its neighbors is either 1, -1, or 0. So you cannot go beyond. So in this case, F gives us a Lipschitz function defined on the graph. Are we okay? And finally, if the target graph H is Z, in this case, the corresponding homomorphism F is called a Z homomorphism. This is also the definition of the language. Okay, so then here is more history about the so this is something beyond counting independences. So now we are talking about homomorphisms defined from the Hamming cube. So after Sapozhenko got the number of independent sets, the next step was to get the number of Z homomorphism from the Hamming cube. And this was done by David Galvin in 2003, and he answering the question of Benjamini, Hakstrom, and Mossel. And in this work, he still used the graph container, which I introduced a few slides ago. So Sapozhenko developed the Sapozhenko graph container lemma, and he used that to count the number of independent sets in the Hamming cube. And a similar technique, not similar, so yeah, I think it's not similar at all, but it's much like more pushed and hard. And he got the number of Z homomorphisms from the Hamming cube. And what was interesting here was there was a bijection between the collection of Z homomorphisms from the Hamming cube to the number of 3 colorings of the Hamming cube. So basically, Galvin's work gave us the asymptotics for the number of 3 colorings on the Hamming cube. So then once we have 3 colorings, then what's the next step? We are curious about what if we have more colors. So after this work, there was a result on the number of 4 colorings of the Hamming cube. This was done by Jeff Kahn and myself, and answering a question of Engels and Galvin. And in this work, so yes, it was so to move from the 3 colorings to 4 colorings, we need an additional component in our proof, which was binary entropy function. And using this, we could get the number of 4 colorings, but we couldn't move forward. So we couldn't get the number of 5 colorings. There were some obstacles. And after this, the more general result was done by Jenssen and Keevash in 2020. So basically, they got a very general result. So they got the asymptotics for the number of H colorings from the m-dimensional discrete torus ZMN. So this is generalization of the Hamming cube. The Hamming cube is the 2-dimensional, Z2n, and ZMN means we have m choices for each coordinate. So this is a generalization of the Hamming cube, and so basically they handled all of the possible homomorphisms when H is a finite graph. So this answers the question of Engels and Galvin, and also they answered a lot of questions in this area. And for this one, they put some more additional components in their proof. So in addition to isochronometry, graph container, and entropy, they also used cross expansion from statistical physics, and also they used some algebraic properties of the discrete tori. Okay, so basically in this work, everything is done for the Hamming cube because not everything, but everything, like all of the things in this line of work was done by Jenssen and Keevash. But we don't stop, so we continue. So then what's the next step? The next step was, okay, then what happens if we just consider the middle layers of the Hamming cube? So the middle layers of the Hamming cube, so it was done by Ballon, Garcia, and Lee in 2020. They got the asymptotics for the number of independent sets in the middle layers of the Hamming cube. And the techniques they used are subsets of the techniques of Jenssen and Keevash. They used isochronometry, graph container, and cross expansion. And I think the reason why I'm interested in the middle layers of the Hamming cube, which might be different from their motivation, but so here in this work, they have to rely heavily on the algebraic properties of this discrete tori. But if we just look at the middle layers of Hamming cube, then suddenly there's no algebraic properties, because it's just like, we have some very nice mathematical object. But if we just look at a subset, not a substructure, we just look at a subset of this mathematical structure, then it's very likely that this part loses the very nice property of the entire mathematical object. So when we look at the middle layers, then we lose these very nice algebraic properties. And then we are interested in, then can we still expect something similar to the middle layers? So something similar, can you expect for the middle layers to have some similar properties as the entire Hamming cube? So that was my motivation. And in this work, they got the number of independent sets, but they couldn't get the number of cube colorings because the reason was, for the independent sets, they didn't need algebraic properties because they didn't need entropy. So in order to use entropy, they needed algebraic properties, and independent sets can be gotten without using entropy method. But in order to get cube colorings, they needed entropy, but without algebraic properties, they couldn't use entropy. So that was the problem. So an open question was this: what is the number of cube colorings of the middle layers of Qn? And the main obstacle was the absence of algebraic properties. Clear, or am I too? Is this okay? Okay, so now this is our main contribution. So again, the main obstacle was the absence of algebraic properties. And then our contribution was, we proved a similar thing without algebra. So our tools is the same: spirometry, graph container, entropy, and closed expansion, but there's no algebraic properties. So basically what we did is to remove the algebraic component from Jenssen and Keevash proof. And the meaning of this work is, now because we removed the algebraic component, so our proof, so currently our result is only for the middle layers of the Hamming cube, because there was a question of Barlow, Garcia, and Lee. But now our proof can be extended to any bipartite graphs not necessarily with the algebraic properties, but it can be extended to any graph with a certain amount of expansion properties. So now our result can be extended to the number of homomorphisms from an expander. So it can be connected to the typical structure of homomorphisms, or approximate sampling algorithms of the homomorphisms, including independent sets or colorings. Okay, so this was our main result. And so this is the end of slides. And so for the rest of the time, I'm going to talk about some of the proofs of our result. But do we have any questions?
The assumption that you have on your graph is that it's some expansion property, or is a parametric properties?
Yes. So expansion, so spirometry and expansion, they are similar things. Yeah. Yeah. That's okay. Okay. So maybe a little bit more, but I think it's not very it's not very restrictive. So yeah. So now the follow-up work of this work is, we are trying to extend this argument for any expanders, and it's going okay. So it seems we just need the expansion properties. Okay. And do we have any other questions? Which one is my water? Maybe this one is mine.
The anti-chain thing, that was motivation.
Oh yeah. Yeah, because anti-chain is so okay. Yeah, so because anti-chain can be seen as an independent set if we define adjacency by inclusion. Yeah, so this one is a motivation for considering the number of independent sets. And basically, this anti-chain proof is done based on the independent set result. Because so in Sapozhenko's work, what he did is that he just considered two layers of the Boolean lattice and showed the result for the number of independent sets here, and they used induction. The extent, because when we have an anti-chain, it can be seen as like we have some occupied vertices here, and then he counted the number of independent sets in the rest of the graph, and he used induction. So yes, so basically his work builds on, so in this anti-chain result, he also used the graph container lemma. So that was the main tool. Okay, then in my proof, because our proof has several components, isoperimetric, graph container, entropy, and cluster expansion. So I don't think I can talk about everything in the rest of 20 minutes. So I have to make a choice, and I chose this entropy. Can I talk about entropy? So how are we already very familiar with entropy? Who are familiar with entropy? Very familiar with entropy, like beyond the definitions. Yeah, I know that you are. Yeah, because we took the same classes. Yeah, we are siblings. Yeah, we are not just siblings. We are. Oh yeah, you're my older sister. We started the same, but yeah, she left early. She abandoned us. Okay, then let me focus on the entropy. And yes. Then can I move this up so that I can use the board?
Computer box.
Yeah, I think we can turn off the computer.
We have the Zoom going.
Yeah.
Oh.
Yeah, just. Maybe we'll leave that on just in case it doesn't come back on.
Are you sure? For the projector.
Okay. Okay.
Want to switch to camera?
Oh, I don't know how to, I don't know how to do that. Sorry. Very poor at technology.
The camera's on now. Okay. So people who aren't there can see this.
Yeah, I think we will.
Okay.
So in the asymptotic enumeration, what we saw was we constructed a very easy lower bound and then showed that that is the truth. And so we're going to talk about some very simplified situation. Let's say G is a bipartite graph. And this is irregular. And this has n vertices. So it looks like this. And also assume that G is balanced. We have n over 2 vertices, n over 2 vertices, and this is irregular. And so we are considering the number of Q colorings. And let's say for now, let's just assume that Q is even. It doesn't have to be, but it's for simplicity. And our claim is to show that the number of Q colorings of the graph G is at sorry, this is not our claim. It's just trivial. This is at least Q over 2 to the n. We divide. It's because, again, to get this lower bound, we just need a construction. So we have Q colors, and we just assign Q over 2 colors in this part and Q over 2 colors the other part. Then we have freedom. Then each vertex can be free to choose Q over 2 many colors. So from this way, we have this trivial lower bound. The number of Q colorings on this graph is at least Q over 2 to the n over 2 squared. So this is Q over 2 to the n many colors. So this is a very, very, very trivial lower bound. And our claim is this trivial lower bound is not very much off. Off. This is very close to the truth. We show that actually the number of Q colorings is 2 over 2. We have this trivial lower bound times 1 plus 3 more. And we're going to use entropy to show this. Okay, but let me make some remarks. So first of all, this little of one term is in the exponents. So this is very weaker than the actual asymptotics, right? So if you want to get some actual asymptotics, then that should be in the form of 1 plus little of 1 times something. But this one has this little one term in the exponent. So if we write it out, then this is q over 2 to the n times q over 2 to the middle of n. And as you can see, this one can be enormous because we have big n here, n rows. So this is very like much weaker than getting actual asymptotics. And we needed all kinds of the tools like graph container and cluster expansion to get down from this logarithmic asymptotics to the actual asymptotics. So we do need some more like hard techniques to get down to actual asymptotics. But because we only have like 50 minutes, so let me just stop. We'll just be satisfied with this thing. Okay, and let's simplify the situation a little bit more. So let's just assume that Q is 4. And then we'll show that C4, the number of form colorings in this graph is what is 4 over 2 to the 1 plus little of 1 times n. So this is not our claim, but our real claim. Will this, and we're going to use entropy for this. Okay, so who knows the definition of entropy? Binary entropy function. Wow, okay, then maybe we'll need 1 extra hour to explain.
You'll see it, we won't forget it as soon as you look at it.
Oh, okay. Yeah, sure. Maybe you've seen this in, I don't know, before I was born. I don't know. And okay, then this is a design for the entropy function. Okay, so by the way, I'm doing probabilistic combinatorics. So I work with random variables. So here this x is a random variable, and not just random variable, but our locally discrete random variable. And so let me say P of x is the probability that this x is equal to small x. And then the binary entropy function is defined the summation x probability of x of 1 over probability of x. This is definition for the binary entropy function, but you don't have to worry about it. So we're gonna just use the properties of the binary entropy function. So we can just forget about the definition. Okay, then what is the binary? Why is this entropy useful? It's because this entropy function gives us kind of like measure of the randomness in our random variable. So for example, one very simple property is if we can compute the binary entropy of the given random variable x, then this is almost log of the range of x. And we can achieve the equality if and only if x is uniformly at random. So for example, if we roll a fair coin, in that case, the binary entropy of the random variable, the coin, is exactly 2, because we have 2 choices. On the other hand, if we roll a fair die, in that case, the entropy of this fair die is 6, because we have 6 possibilities. And as we, intuitively, the more possibilities we have, the more randomness we have. So basically, this reflects that fact. When we have more possibilities, then the random variable has more randomness and or higher entropy. And because of this, we use this, we can connect this to this enumeration problem. So in order to show this, what we do is we consider F to be the collection of all of the 4 colors of G. And then we pick F. So this is a random element of this collection. And we pick this uniformly at random. So this F is a random variable. And in this case, using this, what we can get is if we measure or compute the entropy of this F, then this is precisely log of size of the number of this. And this equality is because this F is uniformly at random. Okay, and then what is this? This is log of C for G. So basically, in order to show this, what we need to show is this claim is actually HF. This is 1 plus little of 1. So once we show this, we are done. Okay, so yeah, so the rest of the proof goes to analyze this H of F, and then we're going to use a lot of properties of the entropy function to bound this entropy of F. But for that, we have to know the properties. Okay, so some of the properties of H of X. Let me make it very brief. So first of all, what we have is the entropy of X given another random variable Y. This is called conditional entropy, and this is at most the entropy of X. And again, intuitively, this means whenever we have some additional information, then the randomness decreases. Okay, so whenever we have, so this Y is considered as some more additional information, and when we have that, then this is lower than the entropy. And then another property is the entropy of XY. This is at most entropy of X plus entropy of Y. Again, when we have, so the randomness in two random variables is at most the sum of their randomness in each random variable. So this is because if the two random variables are not independent, then probably one random variable gives us some information about the other random variable. So this inequality holds, and this is equal to entropy of X plus entropy of Y given X. Again, intuitively, this makes sense. It's just, we are looking at the conditional space, and then the amount of entropy randomness is the same. And
So is it HXY? What does that mean?
oh yeah, okay. So I can give you the definition. So basically, this is conditional entropy. This is summation Y Ty Hx given Y equals Y. And this one means we use conditional probability instead of the original probability.
The second one,
HXY, this one? Yeah, HX. So we have two random variables. Oh, yes. Oh, yes. So this, okay, so maybe we have random vector, it consists of two random variables. Yes. Okay. So this is very, the property is very intuitive, and it's very nice, and it's very so using those properties, we can bound the entropy of this random coloring. So this is where we are heading to in the next 5 minutes, if this is feasible. Can I erase this board? So F, this is a random for coloring of G, and our K is the entropy of F is at most 1 plus little of 1 and over 2. And this at most is enough because we have a lower bound at 1 and 2. So this is our graph G, and this is the regular. Oh, yes, sure. Okay. So how do we bound the entropy of F? So basically, the strategy of us is we open up the information very cleverly, and that's what we can do well, right? Because we're all clever. So instead of opening up this, colorings, so this F means the arrangement or the assignment of the colors of all of the vertices in the graph G. And instead of looking at these colors at once, what we do is to open this up, and we first open up the even part and the odd part later. So then this one is equal to entropy of even part plus entropy of odd part given even part. Okay, so what we do is we open up the colors of even first, and then we look at the odds. And in this case, we already have some prior information about the colors of even part, and we're going to take advantage of this prior information. Okay, and then what is this PE? Okay. So first of all, we found this one first, entropy of FE. Okay, let me first write down this inequality and then explain. This is almost 1 over D times summation BEO, entropy of F, and the neighborhood of B. The meaning of this is, again, instead of looking at all of the colors in the even part, we partition this E by the neighborhood of the odd vertices. So we have this even part, and then each vertex has some neighborhood, and then if we collect all of the neighborhoods of B, then this covers the even part, right? So instead of looking at all of the colors on E at once, we look at the neighborhood of each vertex. But this way, this vertex is covered as many as D ways. So we divide first, sum up all of the entropy, and then we divide it by D because each vertex is seen D times. So intuitive, I mean, this is okay, but I'm not being rigorous, but intuitively, is this okay? This is called Sherlock's lemma. And basically what it does is this, because we measure entropy like locally, but because each vertex is covered or seen D many times, so we divide the entropy by D. So this is what we did, and then how about the second term? This entropy of FO given FE. Oops, I don't have so much time. And this is, again, this is again, instead of looking at all of the odd vertices at once, we just look at this one by one. So this is at most the summation of the odd vertices, entropy of V given the prior information. So instead of looking at treating these odd vertices collectively, we just look at each vertex individually, and this does not decrease the entropy of the entire set. That's the philosophy in this inequality. Okay, and then so we are curious about the entropy or the color of this vertex, but then this, we do not have to need information about the entire even part, because what affects the color of B is just its neighborhood, right? So this is at most, instead of looking at this too much information, you can just look at its neighborhood. And because now we are looking at smaller amount of prior information, so this does not decrease the amount of randomness. Okay, and then again, instead of looking at the color arrangement of the neighborhood, we just need the palette of the neighborhood, because that's what affects the color of B. So this is again at most summation VEO, entropy of this color given not the entire color arrangement, but the palette. I don't know how many L's and E's it has, but anyway. So this means we just look at the palette of the neighborhood of B. And because this is enough to decide the color of B, or the reduced possibility for B. Okay, then once we have this, we do the same thing here. So this means we have B here, and then we have the neighborhood of B here. And this means what's the color arrangement or assignment of the neighborhood. And if we do not have any prior information, then the naive upper bound for this is 4 to D, because we have 4 colors. So theoretically, each vertex can have 4 many choices, right? So the naive upper bound for this neighborhood is 4 to D, but we can do better by looking at the palette first. So instead of considering counting the number of colorings this way, what we do is we open up the palette first and then see how many colors are used in the neighborhood. And then we assign color to each vertex. And somehow this way we can get huge savings. So this is at most 1 over d summation this. Instead of looking at this, we first look at the palette of the neighborhood, and then decide color assignment given the information of the neighborhood. Okay, so we are almost done. So we have, so this is the bound for the first term, and this is the bound for the second term. So we sum them up. So this one gives us entropy of F is at most summation V in O, 1 over D times entropy of F on V. I'm just copying this, plus entropy of the neighborhood given the palette, plus entropy of the color of V given the palette of neighborhood. And then our goal is to say that this is at most 1 plus middle of 1 times F. How many vertices do we have in O? It's not there. Sorry. N over 2. So that means, so this one, this comes, if we can show that this individual term is at most 1 plus middle of 1 times 2, then done. So basically what we're going to do is to give up to bound this individual or localized term by something like 2. And then, yeah. So I don't know, can I continue or maybe I just stop? I don't know. 2 minutes? 2 minutes is okay? 2 minutes? Okay, so then let's do this. So our goal is to show that this one is at most this very specific number. First of all, this entropy is big O of 1. This is a constant number. That is because we have 4 colors. So that means the number of possibilities for this palette is also constant. If we have 4 colors, then it's almost, I don't know, 2 to the 4 is a number. So that entropy was at most log of the range of random variable x. So this entropy is okay and constant. But then because we have this 1 over d term, and d is very large, so this first term is middle of the entire thing, is middle of 1, so it can be negligible. But here the point is, by opening up the palette, we take a huge advantage, but actually the cost for opening up the palette is negligible. So this is the thing, I mean, this is the part that we are being clever. Then how about this part? So this is what happens here. So I'm not gonna be very rigorous, but what happens here is how much advantage can we take by looking at the palette? So if you look at, so for example, if we have like, is it possible that this one is 4, say F and V? Is it possible that this is 4? We have 4 colors, but is it possible that we see all of the 4 colors in our neighborhood? It's impossible because then V has no way to go. So this is impossible. Then what if this is 3? It's possible, right? But then if we see all 3 colors in the neighborhood, then that determines the color of V. So this one is still negligible. Because in this case, maybe the neighborhood, they have more choices, but V itself has no choice. So this does not give us the optimal. So at the end, this sum is much smaller than 2. So we can ignore this case. Then is it possible that this is 2? It's possible. And in this case, each vertex in the neighborhood has 2 choices, and V itself has 2 choices. So this term becomes log 2, which is 1. And this term becomes log of 2 to the d, because each vertex in the neighborhood has 2 choices. So altogether, they have 2 to the d many choices. So we have log of 2 to the d, which is d. but we divide it by D. So in this case, we have precisely 2. And finally, is it possible that this is 1? It's possible. But in this case, the neighborhood has no choices because the color is determined. So this entropy becomes 0 because there's no randomness. Everything is determined. So in this case, this one has 3 choices. So maybe this one has a little bit room, but still their sum is at most log 3, which is strictly smaller than 2. So again, this case is negligible. So the worst case or the best case is achieved when we have this. And in this case, the rest of the terms becomes at exactly or at most 2. So altogether, we achieve this power, and we are done. So I hope this gave you how we can use entropy in this like enumeration problems. And let me finish my talk. Thank you very much for your attention.
Thank you. Let's take questions, but first let me stop the recording. It's very dim.